Okay, I'll start with an example where we find the volume of some region in space using triple integrals, and moreover I'll do it with both cylindrical and spherical coordinates, so that you can see like the difference between the two of them, like regarding how the bounds look like for the triple integral. So what's the region in space we want to compute the volume of? Well, so they give us an equation which is c squared greater or equal to x squared plus y squared. So remember that I'll give you like a list of surfaces that more or less you should know how to recognize. But if you think of this in space, then this region corresponds to like the cones that we have been speaking before, but now like the two pieces of the cone. So it looks like this. Okay. Now then that corresponds to like the points that satisfy the inequality. The idea is like there's like points which are inside the cone and points which are outside the cone, and so the ones that are inside are the ones that satisfy the inequality. How do we see that? Well, let's take a point, for example, here, which is 0, 0, 1. If you do 0, 0, 1, you see that 1 squared, right, is greater or equal to 0 squared plus 0 squared, right? And so this point satisfies the inequality. On the other hand, if you take a point like, let's say that here is 2, 0, 0, right? If you take a point like 2, 0, 0, you get 0 squared, you get here 4, you get 2 squared, which is 4, and then you get 0. So it is not true that 0 is greater or equal to 4. And so what I'm trying to say is that the inside of the cone inside of cone, those are the points that satisfy the inequality. Okay, and so we have this cone, and again remember that the cone in principle will extend indefinitely in both directions. So you should imagine that this is like of infinite size, and so it would just keep growing forever. And so in one of the previous examples, what we did was like take a plane to cut it off, right, so that it would give us something finite. Now instead we will take like a sphere, and we'll just look at the part of the cone that's inside the sphere. So now remember a sphere. This is a sphere center at the origin of radius 1. So you have something like this. And then, well, we just have to put these two pictures together. And the volume that we care about, let me draw again the sphere first. So let's do it like this. So the volume that we care about is a part of this cone that's contained inside the sphere. So this is really the stuff that we want to compute. So, and well, by symmetry, right? Really, the answer is there's as much volume as here as there is below the xy plane. So really, you just have to compute this volume upstairs and then multiply it by 2 if you want to get the total volume. So really, we have to find twice this volume. Okay, and so this is a good place to just discuss before telling you how to do this. This is a good excuse to discuss how do you find volumes using triple integrals. So let's talk about that for a second. So volumes. And maybe let me just write here the equations. I won't delete this picture so that we can keep referring to it. So this was the equation of the sphere, and this was the equation of the cone. So let's put it here. And the idea is that you can find the volume as, so the volume of a region R, of a 3D region R, is just the triple integral over R of what? So remember that for triple integrals, I mean, as for any integral, you have to put like a function that you are integrating. So basically what we put here, if you like, is 1, the function constant equal to 1, but I'd rather just omit the 1 and just look at it from this perspective. So what this is saying is that the total volume of a region in space, if you think of the integral in terms of this approximation with the sums, what this is saying is that you start adding up the chunks of little volume that you get by cutting up your region, and you're cutting it into tinier and tinier pieces. This is like the approximation with the, like, for example, parallelepipeds in the case of a double integral. And so at the end of the day, the volume is nothing more than the sum of all those tiny pieces of volume. The thing is that you're adding infinitely many pieces, and so that's why you cannot just like put like a sum notation here, and you have to use the triple integral. But so useful formula to keep in mind if you want to compute volumes is that you just are really adding up the pieces of volume that make up your region. And so in this particular case, we are going to use this formula. And so let's again, you have to think of this picture as having rotational symmetry about the z-axis, right? And so what that means is that you can take a cross-section of this region. So let's look first at what the cross-section is. And the point of the cross-section is that you cut it with the plane that contains the z-axis and is perpendicular to the floor. So imagine cutting it here, and what you get is upstairs you still get like the z-axis, and now you get another axis, which really it could have been any of the axes that you're using here. It could have been like the x-axis or the y-axis. And so since a particular label that you put is not that important, it's useful to think of this as the r, like as an r-axis, where r represents the r from cylindrical coordinates. And so what you get when you cut a sphere, right? When you slice a sphere, you get a circle. So you get a circle here. And when you cut the cone, we did that before, right? You get something like this. And so from this point of view, maybe the volume, it is more clear what we're doing, what the volume that I'm talking about is. It's just this area that you get here, and then you start rotating it by, I mean, you really only need to take the part to the right of the z-axis, because once you take this piece and rotate it by 2 pi, you recover the full solid of revolution. So really, you only need to look at this piece when we find the bounce. And so let's do this using both cylindrical and spherical coordinates. In fact, this picture is no longer necessary because we only need the cross section. So let me just write again the equations here. So let's set this up first for the cylindrical case. Okay, and so the volume in this case is going to be twice, just twice, because I'm just going to compute a piece above the xy plane. So it's just going to be this times 2, just so that you don't have to worry about finding the bounce downstairs. So it's going to be twice the volume of what? Remember the dv in cylindrical coordinates. Let's write it here. Is r dz dr d theta. So the only thing that when we compute volumes is there's like a constant function 1 in front of the volume differential. So you just have to write here dz r dc dr d theta. And now we set up the bounce. In these problems with rotational symmetry, usually you can even put this bounce from first. In this case, since you're doing a full rotation, you just go from 0 to 2 pi. Sometimes you may go from 0 to pi over 2 or 0 to pi, depending on whether I tell you that you are not looking at a full solid, but only half of it, for example. But in this case, we're working with all of this. And now let's try to figure out like the equations here in cylindrical coordinates. So remember, this equation is the equation for the pink arrow or line is c squared equals x squared plus y squared, which in cylindrical coordinates becomes, remember that c does not change, and x squared plus y squared gives you r squared. And so you get, well, in principle you get plus or minus r, but since we're only looking at the part above the xy plane, you can take c equals r. Okay, and then the other equation that we need is the equation for the sphere in cylindrical coordinates. So the sphere in cylindrical coordinates is this, which again becomes r squared plus c squared equals 1, and that allows you to solve for z, and you say c equals root of 1 minus r squared. Again, there would be like a plus or minus, strictly speaking, but that's not necessary in this case. And the nice thing about doing this cross-section business is that when you take the cross-section, this behaves like y, this behaves like x. So when you're doing the order dz dr, this is like doing the order dy dx. And so remember that when we were finding those orders of integration, we had to use like vertical arrows to find the bounds. And so what I'm saying here is that the bounds, in terms of the vertical arrows, all the arrows start at this line, right, which is C equals R. Let's put it here. And the arrows end on this blue line, which has equation Z equals root of 1 minus R squared. And then you have to put the bounds for R, right? The bounds for R, remember, are the largest and smallest value that R takes in this pink region. So the smallest R is being measured with respect to the z-axis, right? Remember, it's the distance with respect to the z-axis. So what's the? Let's think about this for a second. What's the smallest value that R can take in this region? Well, R can be, I mean, we're including the z-axis, which has distance 0. So R can be 0. But then what's the largest value of R? Well, the largest value of R is precisely here, right? And that's the point where the blue and pink curve intersect. So that's the point where these two equations are the same. So you have to put it here. When these two are the same, you get that R equals root of 1 minus R squared. And so this means that R squared equals 1 minus R squared, or 2R squared equals 1. And so R equals what? 1 over root 2. Okay, so in this case, the bounds for R do not go up to 1, because if you put up to 1, then basically you're ending here. And now that we did that, we're good to go to do this integral. So this gives us 12. Also something that I haven't done before, but it should be reasonable that you can do it, is that since nothing in the first two integrals involve theta, you can sort of do the integration with respect to theta first. And so that just gives you 2 pi, and so you get 4 pi times the integral from 0. Oh, sorry, it should be 4 pi, not 4b. The integral from 0 to 1 over root 2, from R to root of 1 minus R squared of R dz dr. Okay, and again, this gives you, well, you're integrating first with respect to z, so that gives you 4 pi times 0, 1 over root 2. Well, when you integrate dz, that gives you c, and then you have to evaluate at the bounds, so you get r times root of 1 minus r squared minus r dr. Okay? And now we have to integrate this last thing, so 4 pi. Really, you can do it as two different integrals, so integral from 0 to 1 over root 2 of r times 1 minus r squared to the 1/2 minus r squared dr. Okay, so I'm going to do these two integrals separately. The last term is easy to integrate, that's just r cubed over 3. This term, well, if you want to integrate it, you have to make a substitution, like you would call u equals 1 minus r squared, right? And so you're integrating like root of, basically you're integrating like square root of u. So this should be, let's try to do it by hand, but you should work it out with a substitution if you prefer. So this should be square root, let's see, 1 minus r squared times 3/2. So if you just put this, Then the derivative of this would be 3 halves, right? It would be 3 halves times 1 minus r squared to the 1 half times minus 2r. Okay, so I claim we should get something like this. And so now when you differentiate this, it should give you the thing that you have inside here. And so let's see, if you take the derivative of this, you get the 3 halves. The 3 cancels this 3, you get 1 half. And then by the chain rule, you get minus 2r, which will cancel, the minus 2 will cancel this 2 and this minus. And so you get this thing here. And then so hopefully this one's done correctly, otherwise I'll have to record this part again. Okay? And so let's try to evaluate this at 1 over root 2 and at 0. So when this gives you 4 pi negative 1/3 . So at 1 over root 2, this becomes, when you do r squared, that becomes 1 half. So you get 1 minus 1 half. So you get 1 half to the 3 halves. And then this becomes, well, 1 over, well, this is 1/3. 2 cubed is root of 2 cubed, that's, well, it becomes 2 times root of 2. Let me put it like that. And then you have to think about what's going on at 0. So at 0, you put minus the value at 0. At 0, this does not count. At 0, this becomes 1. Right? This becomes 0, so you get 1 to the 3 halves, which is just 1. So minus with minus gives you plus, so you just put 1/3 here. Okay? So in the end, if you prefer, let's see, the volume should be, hopefully, if I did everything correctly, it should be, notice that everything has a 3, so you can pull this out, and so you get 4 pi over 3. And you get, well, this is, okay, good, this is not too bad. This is 1 half to the 3 halves gives you, well, when you cube everything, that gives you 1 over 8, and then you take the square root of that, you get 2 over root 2. So you're getting since we already pulled out the 3, you're getting this one, and then you're getting that one. And so you're getting 4 pi over 3 times, 1 minus 1 over root 2. Hopefully this is a positive number. It should be, because, yes, it will be positive. So you get 4 pi over 3 root 2 minus 1 over root 2. So at least we did get something positive, which is good, because volume should be positive. Root 2 is a little bit more than 1. So at least that makes sense. So let me just write that here somewhere. Let's put it in this corner. Okay, so the video crashed a little bit, but the calculation will work. So let me just repeat what I was saying in the video that now you're not watching, but we want to compute the volume in spherical coordinates. Using cylindrical coordinates, we found the answer to be this one. Okay, now remember that the differential for volume in spherical coordinates is rho squared sine of phi d rho d phi d theta. So the volume will be twice, because remember we're just looking at the stuff above the xy plane, twice the integral of rho squared sine of phi d rho d phi d theta. And so we have to find the bounds for each of the variables. Again, for theta it's pretty easy because it's a solid of revolution about the z-axis, so theta just goes from 0 to 2 pi. For the others, we have to understand first the equations in spherical coordinates. So if you look at this equation of the sphere, which was x squared plus y squared plus z squared equals 1, basically spherical coordinates have been cooked up so that the equation becomes just rho equals 1. Because this means all the points whose distance from the origin is 1, and this is precisely what is meant by this equation. So the blue curve becomes rho equals 1. And then we have to understand in spherical coordinates the equation of the cone, which we had done in the past, so let me just repeat it quickly here. You just get the rho squared cosine square of phi equals rho squared sine square of phi cosine square of theta plus rho squared sine square of phi sine square of theta. Right, that's what happens when you rewrite each of these variables in spherical coordinates. And so you can factorize rho squared sine squared, and you get a cosine squared plus sine squared, which becomes 1. So you get the rho squared cosine square of phi equals rho squared sine square of phi. And so you cancel the rho squares and take roots, and then you get cosine of phi equals sine of phi. And so again, this is a calculation that we did in the past, so that's why I'm doing it a little bit faster. What this is just saying is that in spherical coordinates, this is just the equation of phi equals pi over 4. So the point of working with a cross-section is that spherical coordinates under this cross-section behaves very much like polar coordinates would have. And so for finding the bounds of rho, it's like finding the bounds for r in polar coordinates. You just use rays that emanate from the origin. Notice that they all start at 0, so you put here rho equals 0 as the lower bound, and they all exit through the blue curve, which has the equation rho equals 1. So the bounds for rho are just from 0 to 1, and notice that in this case it does not depend on the previous variable. And then phi is just the smallest and largest value that the angle takes in this region. The angle starts at the z-axis, so it starts with z equals 0, and then you just drop up to pi over 4. And so the angle is from 0 to pi over 4. And so the integral that we have to do, again, is fairly straightforward. In this, actually, is more straightforward than the cylindrical case, as you'll see in a second. When you integrate with respect to theta, you just get 4 pi. The integral from 0 to pi over 4. The integral from 0 to 1 rho squared d rho d phi. This gives you rho cubed over 3. Oh, and I forgot to write the sine of phi. Right, this just gives you 1/3, which is good. That will give you the 4 pi over 3 that we had before. The integral of this is cosine, or negative cosine rather. And so at negative, you get the answer to be 4 pi over 3, negative cosine of pi over 4, which is minus 1 over root 2. Minus with minus gives you plus, so you get plus 1. and that's precisely 4 pi over 3 times times root 2 minus 1 over root 2. So you get the answer that we had found before using cylindrical coordinates. So this is a good example that shows that despite the fact that spherical coordinates look more intimidating in general, they can actually give you the same calculation in a shorter amount of time, depending on how compatible the equations are with the spherical coordinates.